Alright, in this video I'm going to do two examples of talking about whether a function is even or odd and how we can tell by the symmetry of the graph, and then how we can confirm algebraically as well. So remember that an even function always is going to have y-axis symmetry, and an odd function is going to have origin symmetry. So let's say I look at this first function, f of x equals 3 over x squared. If I graph it on my calculator to take a look, I could type that in, 3 divided by x squared. And I see that the function looks something like this, and just from looking I can tell that that has y-axis symmetry, which is going to tell me that that is probably an even function. So I've got my claim here that I think this is an even function, but a lot of times we're going to be asked to prove or to justify algebraically that something is either even or odd. So let's think about the definition of an even or odd function. An even function, we know that f of negative x is equal to f of x. So when I plug in negative x to my function, I should end up with, when I simplify, the original function itself. For an odd function, f of negative x equals negative f of x. So when I plug in negative x to my function, I should get the opposite of the original function after I simplify. So we think that this function right here is even just by looking at the picture. I didn't check that every single point is across the y-axis, but just by looking it looks like it has that type of symmetry. So let's go ahead and check by actually confirming algebraically by finding f of negative x. So f of negative x would be equal to 3 over negative x squared. And if I simplify, when I square this negative x right here, I'm going to end up with a positive x squared. So f of negative x is equal to 3 over positive x squared. And I notice that this is actually the same thing as my original function. So this right here is f of x. So I've just proven that f of negative x is equal to f of x itself. This would be an example of a proof or confirming algebraically that this is an even function. Now let's take a look at what might happen with another type of function. So here's a second function, 3x cubed plus 4x. If I want to go ahead and again graph that on my calculator to give myself an idea, I've got 3x cubed plus 4x and you can see that this is not having y-axis symmetry this time. This time it looks like I have origin symmetry from looking. So origin symmetry means we've got possibly an odd function. Origin symmetry means it's going to be an odd function. Since it looks like origin symmetry, it probably is an odd function. So let's think. If I need to confirm this algebraically, that means I'm trying to prove that f of negative x equals negative f of x, like we mentioned before. So let's find f of negative x. 3 times negative x cubed plus 4 times negative x. If I simplify, f of negative x is equal to, well, a negative x cubed is going to be negative, so that negative can come out front, and I'm going to have negative 3x cubed. And a positive 4 times a negative x would be a minus 4x. So already from looking, I'm noticing that each of these terms is the opposite of what I started with. So I have the opposite or the negative version of this function f of x right here. If I want to show this by factoring, doing the opposite of the distributive property, I could pull out a factor of -1 from my expression. The first term would leave behind 3x cubed, and this would leave behind a positive 4x. And let's check if I redistribute that, -3x cubed minus 4x. That's the same thing, I just factored out a -1. So I've shown here that I have -1 times my original function f of x, or f of -x is equal to a negative, my -1 times f of x. And there we go, we've confirmed algebraically that this is in fact an odd function.